to the organizers, and thanks for that introduction. So before I begin, I want to acknowledge that it's Martin Luther King Jr. Day in honor of Dr. Luther King Jr., and I thought I would read a quote from his acceptance speech for the Nobel Peace Prize. This was in late 1964 in Oslo. This is an excerpt, and I apologize for having to excerpt the speech. Previous to this, he's sort of wondering why he's being awarded this prize now when he feels like that the work that he's been doing, the advocacy, is still very much underway and hasn't quite achieved all of its aims. But anyway, I like this section. I accept this award today with an abiding faith in America and an audacious faith in the future of mankind. I refuse to accept despair as the final response to the ambiguities of history. I refuse to accept the idea that the isness of man's present nature makes him morally incapable of reaching for the internal oughtness that forever confronts him. I refuse to accept the idea that man is mere flotsam and jetsam in the river of life, unable to influence the unfolding events which surround him. I refuse to accept the view that mankind is so tragically bound to the starless midnight of racism and war, bright daybreak of peace and brotherhood can never become a reality. I have the audacity to believe that peoples everywhere can have 3 meals a day for their bodies, education and dignity, equality and freedom for their spirits. I believe that what self-centered men have torn down, men other-centered can build up. I believe that we shall overcome. This faith can give us courage to face the uncertainties of the future. It will give our tired feet new strength as we continue our forward stride toward the city of freedom. When our days become dreary with low hovering clouds and our nights become darker than 1,000 midnights, we will know that we are living in the creative turmoil of a genuine civilization struggling to be born. So I thought that might be a nice sentiment to start. Growing up in the U.S., we learn about Dr. Martin Luther King as a hero of the civil rights struggle. But something I only learned as an adult is that in his time, he was quite a controversial and divisive figure. And anyway, but of course, a real inspiration. So I don't have a great transition from that to what I'm actually going to talk about, but except to say that this is one of the very few federal holidays we have in the U.S., and I appreciate your time and being mindful of your time. I'll get going. Okay, so I'm maybe representing the mathematical community in this conference. I'm an emissary from the mathematical community, and folks here who are experts on certified programs and proofs might be aware that mathematicians are increasingly excited about prospects of computer formalization to tackle really cutting-edge, interesting mathematics. So I thought I'd highlight some sort of recent successes that involve either very long and difficult proofs with a lot of technical detail, like the odd-order theorem, can help resolve ambiguities in the refereeing process. So the FlySpec project, which was launched by Tom Hales to formalize his proof with Ferguson of the Kepler conjecture, was in part born out of frustration from the human trying to certify that the proof was 100% correct. Famously, Peter Schulze proposed the liquid tensor experiment, where he challenged the formalization community to verify a proof that he wasn't sure about and wasn't sure that anybody else would actually check because it was sort of so technical. And a final recent achievement is a formalization of something called the Brunery number. This is a bit different flavor than the other things. What was actually formalized in cubical agda is a proof that something called the fourth homotopy group of the 3 sphere, so this is some algebraic invariant of a topological space, was z mod nz for some n. So this was a proof in Guillaume Brunery's PhD thesis in a cubical variant of homotopy theory that satisfies, I can never remember if I'm supposed to say normalization or canonicity, but the thing that means that each natural number has a canonical form. And so then Axel Lundström and Anders Mortberg, formalizers, asked cubical agda what n was, and they said that n is -2, which is wonderful because that was correct but unexpected. So -2z is isomorphic to z mod 2z, so -2 was the correct answer, and unpacking the mathematical construction, one could see that it have been -2. They were expecting the answer to be n equals 2. Okay, so what I actually want to talk about is the 2 formalization projects that were mentioned in the introduction, both of which have been launched since then. So the efforts I highlighted on the previous page were concluded in 2022. More recently, I've become curious about what it would take to formalize results in my own field, which is something called infinite dimensional category theory. And I think there are some in formalizing results in infinite dimensional category theory. And so the first part of this talk, I'm going to try to keep this at a high level because it's difficult enough to explain to a mathematician what an infinity category is. A lot of mathematicians are intimidated by infinity categories, and I don't want to get bogged down in the mathematics. So speaking somewhat metaphorically and at a very high level, I'm going to try to describe some of the particular challenges of taking a recent paper in the infinity categories literature and giving a computer verification of it, so formalizing any of its results. And then I'm going to describe the two particular projects that are attempting to do this, not yet for the sort of cutting edge literature, but at least for the background theory that would be necessary to even formalize the statements from the literature. The first one is in Lean. This is being co-led by Mario Carneiro and Dominic Verity. The second is in RESC, or RZK, a proof assistant written by Nikolai Kudasov. Jonathan Weinberger helped launch that project and spoke about it here last year. Okay, so let's go ahead and begin. So I'm going to use a metaphor to describe what makes the literature in infinity category theory a little bit more challenging to formalize. This metaphor doesn't quite fit, and so I should apologize to Terry Tao at this stage. But nevertheless, this is an interesting idea, so let's discuss it. So here's a famous blog post from maybe a decade ago, titled "There's More to Mathematics Than Rigor and Proofs," that describes mathematical education into three stages. There's a pre-stage where mathematics is sort of informal, arguments are sort of fuzzy, intuitive, hand-waving. We don't necessarily have precise definitions. The emphasis is more on computation and theory. Then there's the rigorous stage, which is what in the US somebody would encounter only in the course of doing a mathematics degree at university. Maybe in other parts of the world it's touched a little bit. And one is taught that in order to do maths properly, one can think in a much more precise and formal manner. The emphasis is primarily on theory. One is expected to be able to comfortably manipulate abstract mathematical objects without focusing too much on what such objects actually mean. This could occupy the later undergraduate and early graduate years. That's maybe the stage that's sort of closest to formalization, but still mathematics is pretty informal. And in the US, you're not really taught necessarily logic, sort of formal logic. And, so I like to acknowledge that, when I earned my PhD, I could not have stated the axioms of set theory. I might be able to do it now. So, rigorous stage. And one has grown comfortable with all the rigorous foundations of one chosen field and is now ready to revisit and define rigorous intuition on the subject, but this time with the intuition solidly buttressed by rigorous theory. So the emphasis is now on applications, intuition, and the big picture. The stage usually occupies the graduate years and beyond. And for Tao, this is really an aspiration. This is an ideal state to reach where every heuristic argument naturally suggests its rigorous counterpart and vice versa, where one's intuitions are so refined that one can dream in heuristics and then later verify that dream through a rigorous proof. So I'm going to use this as a metaphor to describe some of what's going on in the literature of infinity category theory. Again, it doesn't quite fit, but what does seem to be common is arguments are not always explained in full detail. Some claims made as part might not quite be true as stated, but nevertheless, most of the results are basically right. So proofs with gaps or errors are often what's called morally correct. So there's, contain an important idea, and that important idea, even if the proof that was written and in some cases published is not the correct proof. And in particular, proofs in the literature may rely on sort of incomplete definitions, sketched arguments, or explicit unproven conjectures. And I'll illustrate now with some sort of case studies of this from the literature. The notion of infinity category sort of has a long history, but maybe in its modern form, 2003 preprint on infinity topoi. This is the precursor to Jacob Lurie's book, Higher Theory. And what's interesting about that preprint, which can be found on the archive, is it avoids using a precise definition of an infinity category. So this is a 100-page paper that is in the background theory of infinity categories to be used to do something else. derived algebraic geometry, but it doesn't sort of start the way that mathematicians are comfortable, which is here's a definition, and now from this definition we can prove what. So paralleling Jacob Lurie, I'm going to avoid telling you what an infinity category is right now. Very roughly it's a weak infinite dimensional category. Here's what Lurie actually writes. So we will begin in section 1 with a theory of infinity categories. This theory that didn't really exist at the time. There are many approaches to the foundation of the subjects, each having its own particular merits rather than singular. One of those foundations here, we shall attempt to explain the ideas involved and how to work with them. The hope is that this will render this paper readable to a wider audience, while experts will be able to fill in the details missing from our exposition in whatever framework they happen to prefer. The parlance of the field, one uses the term model to describe a precise definition in the traditional foundations of set theory and logic of an infinity category theory. This is what Lurie is trying to avoid using. And a paragraph like this is very common. A lot of papers in the field start exactly this way. However, the book Higher Topos, the long version of this paper, doesn't do this way. Pushback from the community, how can we be doing rigorous mathematics if we aren't even starting from a clear definition? And so Lurie does pick a model in that book. But what's interesting about this is this is sort of the perspective that experts in the field would often prefer to take. So work without an explicit definition. Maybe for aesthetic reasons, maybe because it's so far from their intuition somehow. Okay, so another example called the cobordism hypothesis. This is explaining a little bit about but in an expository article on the subject, Dan Fried writes, this was conjectured by Baez and Dolan in the mid-1990s. It has now been proved by Hopkins, Lurie in dimension 2 and by Lurie in higher dimensions. There are many complicated foundational issues which lie beyond the definitions and the proofs, and only a detailed sketch has appeared so far. And what the footnote elaborates is that nevertheless we use synonyms in this manuscript. The foundations are rapidly being filled in, and alternative proofs have also been carried out, though none has yet appeared in print. And so this is like a fun question to ask among your friends in the field: is has the cobordism hypothesis been proven? And nobody has any clue, few people are willing to go on the record because, of course. So the preprint of Lurie that Fried is referring to, very beautiful ideas and has a lot of gaps in it. And so is that a proof? What is sort of the status of the mathematics here? Does it make sense to try to prove the cobordism hypothesis? And this is uncomfortable for mathematicians, of course. We like to think that our proofs are black and white. But this is an instance that certainly is not. Okay, so another example. A lot of what infinity category theory is for something called derived algebraic geometry, which is a hard version of modern algebra. There's a 2-volume series published in the Society in the last few years by Gates, and Rosen. It runs to nearly 1,000 pages. And much of this first volume is devoted to developing the necessarily preliminary results in, I was trying to avoid this, but when I say infinity category, that's really a nickname for what's more properly called an infinity category. And then there's other versions of weak infinite dimensional categories called infinity 2 categories. It includes this following disclaimer. Unfortunately, the existing literature on infinity 2 categories does not contain the proofs of all the statements we need. We decided to leave some of the statements unproved and supply the corresponding proofs elsewhere, including the proofs here would have altered the order of exposition and would have come at the expense of clarity. And then there's a sort of a clear list of 7 unproven statements. So, so here's a massive book that's resting on conjectures largely, and nevertheless is an important contribution to the field. And the final example, perhaps the most famous of all of those, is from a 1991 paper of Kapranov and Voivodsky. Concerns something called the homotopy hypothesis. Again, I'll avoid discussing the mathematics, but gives a precise definition of an infinity groupoid, which is closely related to an infinity category, and aims to connect it with something from topology called a homotopy type. And this paper contains, it's relatively short, maybe 18 or 19 pages by mathematics standards. We don't tend to have page limits in our journal publications. But 7 years later, Carlos Simpson posted a preprint which shows that a particular homotopy type cannot be realized by a particular 3 groupoid, so a truncated version of an infinity groupoid, and this contradicts clearly the statement in the infinity or in the corollary, the last corollary in this paper. But what was confusing about it is Simpson could not identify where Pranoff and Voivodsky went wrong in their proof, and Voivodsky, at least, who's the one who's the source of this anecdote, who's written about this, says, he thought that the sort of obstruction that Simpson is identifying with in their argument. So it was very obvious from the 2 statements of mathematics, but neither party could identify whose proof was wrong. And Voivodsky said, I was sure we were right until the fall of 2013, so 15 whole years later. And this and another sort of famous mistake in some of Voivodsky's Field's metal work on motivic homotopy theory actually led him to abandon pen and paper mathematics and pursue computer formalization. So, and in fact, pursue computer formalization in a novel foundation system, which is something that I'll come back to a little bit later. Essentially because he didn't trust the mathematical community, because he had such a strong reputation, because he earned a Fields Medal in 2002, he didn't trust the mathematical community to check his proofs, at least quickly enough. Mistakes discovered eventually. As a working mathematician, I guess you want to know as soon as possible. And so turn to computer formalization. Okay, so here's the reason why I'm discussing these anecdotes is I want to think about the following question. So, how might this literature, and so I'm using infinity category theory both as my personal area of expertise, but also as a stand-in for other subfields of mathematics that are similarly complicated and technical and involve very long papers and involve very complicated definitions that aren't often stated in full. So there are areas of mathematics that are like that. There are other areas of mathematics that are not like that. But how might this literature read differently in a future where mathematicians are expected to work interactively with a computer proof assistant? So is it possible to use a computer proof assistant if your literature is sort of post-rigorous? It's not explaining everything all the way down to the foundations. How could you possibly formalize something like that? So I don't think the prospects are quite as bleak as you might think. On the one hand, it's desirable to give a precise construction of a mathematical notion of an infinity category. So that was the preprint on infinity topoi. The desire was to develop this without a precise definition. One could instead axiomatize the necessary properties of an infinity category and then try to prove theorems regarding those properties and then hope that the theory is not vacuous. So eventually you would have to construct something that satisfies those properties, but maybe you could sort of black box that using this technique of axiomatization. That's quite a common technique in formalization as well. So a sketch proof, like the proof of the cobordism hypothesis, would be harder to implement because proof assistants tend to require some. But certainly if one made the effort to formalize a sketch, it would make it a lot in the proof. So Lean, for instance, and many other proof assistants allow saris, where you state a theorem but don't supply the proof yet. And one could imagine this would be an appealing way to both reward the mathematicians who are involved in constructing the scaffolding, which is quite hard, a sketch program, but also reward the mathematicians who are involved in filling in the saris, so completing the details of the sketch that are required to make it true. I think that's a very important sort of sociological problem within mathematics, is figuring out a way to give credit to everybody who was involved in a team that's needed to achieve something difficult, like the cobordism hypothesis. The Gates-Square-Rosenblum book, Proof, Modulo, and Proven Conjectures, again, should be formalizable, providing that those conjectures are clearly stated in exactly the way that they are used. That, I think, more or less is what is happening, at least informally, in this book. And then finally, of course, an incorrect proof should not be formalizable, which is, of course, a good if every mathematical journal publication is required to come with a formalization, one would imagine that would cut down the rate of mistakes in the literature, though of course not completely eliminate them. Perhaps this process of formalization would help identify the error by calling attention to a subtle obstacle to be overcome. This last point is somehow persuasive because the fundamental problem in the field is that how do we formalize proofs in an area like my own where the arguments tend to be long and complexity every step. So even today, his proof with Kapranov of their claim of the coborders is the one that's a mistake. But still, there's an active debate on precisely what the mistake is. There's I'm not one of the other long math overflow posts where mathematicians are still trying to figure out exactly what happened here. And it's, not that this is an obscure area that nobody's thought about for the last 30 years. This is a subject that is of central interest to people in the field. And nevertheless, it's just the ideas are so long and so complicated that no one's quite gotten to the bottom of it yet. So do we as a community really need to just slow down and do everything formally so that we don't make mistakes and every conjecture is, is proven correctly? We are eliminating the mistakes in the literature. How does that integrate with Tao's vision for post-rigorous mathematics, where some mathematicians are dreaming up vast research programs that are beyond what is provable, what is formalizable, but involving definitions that are not yet made precise that then sort of lay the groundwork for the future? Do we all have to return to doing our mathematics rigorously in a computer proof assistant? I think that's an interesting question. And so more recently, I've been involved in some experiments to try and formalize some infinity category theory in a computer proof assistant. And I'll describe sort of three broad strategies for sort of proceeding nevertheless to try and get a toehold on this literature. So the first strategy I might call analytic, giving a precise definition of an infinity categorical notion in some model. So the probably most common model is something called quasi-categories and prove theorems using the combinatorics of that model. So really start from a definition that is made precise in set theory and then tie every step of the argument down to the traditional foundations. A second strategy is this axiomatic one. So if it's objectionable to use this definition because somehow the aesthetics are wrong or you're forced into considering combinatorial details that get in the way of understanding the ideas of a proof. Instead, we could axiomatize sort of the theory of infinity categories or the category of infinity categories. One approach to that is something called an infinity cosmos, which I developed with Dominic. And then we could state and prove theorems about infinity categories in this axiomatic language, and then hope later to show that the theory is non-vacuous by proving that some model does satisfy the axioms and formalize other examples as desired. And then a final strategy is the foundations. So, really the fundamental problem here is that, the basic notion of the field, an infinity category is just an awkward concept to define in the traditional set-based foundations of mathematics. An infinity category, I realize I still haven't given you a definition, but it just doesn't involve a lot of sets. And so perhaps we could develop some sort of domain-specific formal language, domain-specific type theory that allows one to have primitive objects that are much closer to infinity categories, to think about infinity categories synthetically. So one would then need a computer proof assistant that implements that specific foundation, that knows the rules of that formal system. So this couldn't be done in something like Lean, but it could be done in an experimental proof assistant, for instance, something like Rusk. And so what I'll do now is describe, so I don't know of anybody who's really working, well, sorry, there are a lot of individuals who are working on strategy one. I don't know of sort of a large group effort towards strategy one, but I've been involved in projects working towards strategy two and strategy three, and I'll talk about those in turn. To the organizers, does it make sense to pause for questions now, or? it might be better. Sure, no problem. Does anybody want to ask a question before we get into the projects? Sure.
What's the difference exactly? Sorry, it was just... What's the difference exactly between strategy 2 and strategy 3? Because it looks like similar to me.
Great. So thanks for that question. In the past, I've described both strategy 2 and strategy 3 as synthetic in opposition to the analytic strategy, which is strategy. The difference is that strategy 2 is something that's implemented in traditional foundations. Really, it's independent type theory because Lean is independent type theory. Lean and, well, the definition of an infinity cosmos is stated in the language of ZFC, whereas in strategy 3, we're giving a definition of infinity categories that is not interpreted in ZFC, but in something else. Explicitly, it's a simplicial extension of homotopy type theory. So it's whether we're working in traditional foundations, whether we understand that as set theory and logic or Martin-Look-dependent type theory with extensional identity types, or whether we're working in some exotic foundation that's optimized to be the foundation for all mathematics.
Well, maybe this question's a bit premature and you'll get to this, but this third strategy, something like cubical AGDA, they take different foundations and tweak AGDA so that but cubical AGDA wouldn't be something that this would fit.
Yes, so great. So you're right. The sort of proof assistant you should think about for strategy is something like cubical AGDA. So, cubical AGDA is implementing a theory, cubical analog of homotopy type theory. It's not cubical AGDA, it's of it that is, I don't believe, implementable in cubical AGDA, but there's some cubical AGDA experts here. You could ask about that later. But something like cubical AGDA. No.
Yeah. So also for strategy 3, how do you then address the gap between the bespoke proof assistant and then the theory of that type system, and then showing that is actually modeling the set-based models?
Right. So you're anticipating a question that appears on the final slide. So on paper, we do understand the semantics of this system. So on paper, I believe it, but has any of that been formalized? No. So, okay, great. Let's dive in. So, okay, so this first project is a formalization project in Lean. It's relatively new. It was launched just this past fall, co-led by Mario, who's here, Dominic Verity, and myself. And the objective is to formalize a particular axiomatic approach to infinity category theory in Lean's mathematics library. So the advantage is we get to take advantage of this large library that exists already. So there's sort of a common workflow used for Lean formalization projects that was developed initially by Patrick Massot. Pietro Montecone is the one who helped us set it up for this. So there's a website, link is there. The website hosts both the Lean Kyle's are a relatively up-to-date copy of math plus. There's also something called a blueprint, what that created from a LaTeX file that's annotated with tags that connect definitions and theorems to formalizations where they exist and indicate dependencies in any case. This produces a dependency graph, which will indicate which results are ready to be formalized, not yet ready to be formalized, in process of being formalized, and so on. And then we have our own channel on the Lean Zulip chat where we discuss all of these. So this is Lean formalization projects. I'm going to get a little bit into the mathematics to try and describe now the idea of this project. So this is the Lean definition of an ordinary one category, so an ordinary category. So in Lean, types are sets for those who distinguish between those notions. So it has a type or set of objects B. Then it has a dependent type of arrows. So between any two objects x and y, there's a type hom x y of arrows from x to y. There's two different notations for that in Lean, unfortunately. So there's COM-XY notation, and there's also X long arrow Y. They both appear on this slide. And then it makes that into a category as additional action. So the data involves a specified identity arrow X to X for every X, a composition function that takes an arrow from X to Y and Y to Z and composes return from X to Z, rules about identity laws and associativity and so on. Okay, so this is the definition that exists in Lean. So the idea of an infinity category is just to replace all these types by something called an infinity. These are also known as types. This also known as anima. It's essentially the information of a topological space encoded by its homotopy groups. Probably weaken all the axioms. What's you can't do, though, is just implement that sketch in this sort of style. So part of it would involve a sort of infinite amount of data. So we have not only objects and arrows, which you might think of as arrows between arrows, and all the way up. But sort of the main issue is really this weakening. So there's really sort of no longer a canonical identity arrow necessarily, or a canonical composition function. Instead, there's a whole bunch of different things that are equally well could be considered as the composite of two different arrows in dimension 5, for instance. And either arbitrary choices and then exhibit a bunch of additional data that exhibits that those choices are suitably coherent, or avoid making the choices and then argue that these things are sort of suitable and deal with the fact that sort of place some sort of homotopically unique relation. So no definition style this in a and in fact is already in Mathlib is a sort of an analytic version of this. So this is a precise definition that's easy to state in traditional foundations that does capture this idea. This is something known as a quasi-category, and here's the definition, which I'm not going to explain at all. The thing that I want to emphasize is that how this relates to the idea on the previous page is not at all clear. So the idea on the previous page is that an infinity category should be just like an ordinary category, except you replace all these sets by infinity groupoids. An infinity groupoid, by the way, is a complex which has some sort of similar analytic definition. And explaining sort of what the infinity groupoid of objects in a quasi-category is, or what the infinity groupoid of morphisms between two objects, or what the infinity groupoidal composition functions are. I mean, these constructions are all a bit complicated. They're certainly known to the expert field, known on paper, but none of this has been formalized. And just the fact that all of these very basic things are a little bit fiddly is the main challenge of this approach to formalization. Involved in every single thing that you want to do. And a sort of fun illustration of the fact that, like, basically no theory of infinity categories using quasi-categories have been formalized for these Mathlib for at least a year is actually last week Joyal and Lurie discovered that the definition of con-complex it included it included an extra horn that should not have been there. And had anybody done anything with this definition at all, we would have discovered that, because there would be no example. None of the known examples of con-complexes would have satisfied that definition. So anyway, I think that's pretty funny. Okay, what are we doing instead? So the idea is that we're going to leverage some of the existing results that have been formalized in Mathlib. So not stuff about infinity category theory, but stuff about other versions of category theory. So there's a lot of ordinary category theory in Mathlib. There's also some development of category theory. There's also some enriched category theory. And we're going to, as much as possible, lean on those existing results to formalize some infinity category theory. And the way this is achievable is that by abstracting the theory of infinity categories using this axiomatic notion called an infinity cosmos. And what it is in particular is it's a particular sort of enriched category whose objects are infinity categories. And from particular 2 category, whose objects are infinity categories, whose morphisms are infinity functors, whose 2 cells are infinity natural transformations. This is an analogy to a 2 category whose objects are ordinary categories, ordinary functors, ordinary natural transformations. And some of the theory of infinity, so adjunctions, limits, conextensions can be defined just using this 2 category. And in fact, some of these definitions are already in MATLib. So this is sort of a geodesic to some significant mathematics results. What will be difficult is sort of showing that any of this is non-vacuous. So, for this to really apply to an actual infinity categories, we need to connect it at some stage back to one of these models, one of these sort of analytic versions, and proving that quasi-categories finds an infinity cosmos will be quite difficult. But my vision is that we'll create sort of a bounty of this, a bunch of theorems that will follow as corollaries. And there are people who are working on pieces of this. Jack McEwen is close to one of the important steps. And so, I think this will be achievable, maybe with sufficient motivation. And the sort of technical homotopy coherence work would be done in showing that this analytic notion satisfies these axioms rather than every single proof of every single thing. That's the vision in any case. So we started this project in September, and the first aim was just to formalize the definition of an infinity cosmos. So it's a particular sort of enriched category, but it involves particular sorts of enriched limits. Those limits do not yet exist in MATLib, and that's what we've done. So here's the full definition. I'm not going to attempt to read it, but it's not terrible. Of course, it refers to some concepts that we also had to formalize. Another thing that we've been doing is I'm learning by some painful experience that if you try to wait till you finish the proof and then get to MATLib, it will never, actually the PR will never complete. So Mario and I formalized the proof that cat has limits over the summer and that we're still trying to PR it. So we've been shipping things out right away. So this definition is not yet in MATLib. I don't know that anybody cares about it yet except us, but the supporting mathematics that went into this definition we have been PRing, so I'm pleased about that. Okay, so this I know is super technical, so I want to kind of conclude this section by coming back down to earth and mentioning some of the things that I've been unhappy about in the formalization so far that are at a lower level. So some challenges that I would love it if the real experts in computer proof assistance could help. So I think we're having a little bit more difficulty with lean than some people who are also trying to formalize quite technical mathematics and other subject areas are. And I'll mention 2 instances of that. So one of the things that Mario and I did, so this is something that we've formalized that is in MATLib right now, is a particular adjunction involving some of the free category and underlying reflexive quiver functors. So it's an adjunction between particular categories. What's distinct? So one of these categories is cat, and the other one is this category of reflexive quivers. And in both cases, the objects are sort of type classes that represent some sort of more elaborate structure. So it's the type of objects that has by inference, some sort of category structure attached to it, and so on and so forth. And this seems to be very confusing for lean. So there's kind of 2 perspectives on a functor. Often, either in lean or in mathematics, sometimes you think of a functor as being a very big thing. You have some sort of big category, some mathematical world that you're working in, and use a functor to transport into some other category. From the perspective of this formalization, a functor is a pretty small thing. It's just a morphism in the category of categories, and going back and forth between those 2 perspectives seems to be very confusing. So what I've circled here are all of so this is a proof that some diagram in the category of categories, some composite in the category of categories is equal to some other functor in the category of categories. That's what this is a proof of. And what I highlighted are all the steps that I think are unnecessary. So telling lean essentially that a functor is a functor and a composite of functors is a composite of functors and the identity functor is the identity functor. And really, I need to interpret this as a morphism between reflexive quivers and not just between the underlying types and so on and so forth. So these are the steps that I would love to get rid of. This is the thing that not a domain expert who's not an expert in formalization has never been able to write this. I needed Mario to come up with any of this code. Okay, so another challenge, so we're in the phase of the Infinity Cosmos project where we're trying to construct this 2 category of infinity categories. And once we're there, then we just apply proofs from 2 category theory to develop infinity category theory. That's great, and I don't know how easy that'll be in formalization, sort of for the following reason. So, Lean is really based on dependent type theory, and let me start with paper. So on paper, a 2 category has something called a 2-cell. These are these sort of 2-dimensional arrows that I've drawn here. And a 2-cell has a boundary involving some 1 cells. Those are the 1-dimensional arrows and some objects. And in Lean, these 2 cells belong to a dependent type indexed by these boundary 1 cells and then also by the boundary objects. And on paper, when you see a picture like this, you can just sort of look at it and say, well, all the 1 cells sort of point in the same direction and all the 2 cells point in the same direction. So a main theorem in 2 category theories, there's a unique composite 2-cell encoded by this pacing diagram. But in Lean, it's not even clear that sort of 2 cells that are in this diagram are composable with one another because they belong, because there's sort of a non-trivial equality between the boundary 1 cells in sort of the case that I've highlighted here. So over the summer, I wanted to formalize a proof that if you have this particular pacing diagram and the etas and epsilons are the units and co-units of an adjustment, then in the middle, what you have is this eta 2 and epsilon 2, that's a unit, and it just cancels, is replaced by an identity and disappears. This some implication for something called the theory of mates. This is about critical composition of mates. So this is a formalization in MATLAB, and I wasn't able to formalize a proof in that style because of this issue involving dependent types and sort of boundary equalities, and promoting those to data or transporting some 2 cells, something like that. Instead, I had to sort of pass to the components of the natural transformations, but that means that this is than it should be. So we prove this for a particular 2 category of categories where 2 cells have components, but not for all 2 categories. So I mentioned this challenge in a talk last week at Lean Together, and this particular case has been solved, but there's a lot of cases like this, and in general, reason 2 cells is something that would be really and let me now go into the final project, which is to explain this synthetic approach to infinity category theory in RESC, and then I'll take some questions at the end. So again, I explain a little bit the sort of mathematical idea. So infinity categories are sort of like categories where sets are replaced with infinity group arrays, but it's just really difficult to turn that into a precise definition in the traditional foundations of mathematics. It takes a very long time to explain what an infinity groupoid is. That's what Kapranov and Voivodsky were trying to do in that paper, and we still don't know where they made a mistake. So it's hard to give a precise definition of an infinity groupoid. However, in other foundations, sort of type structure, type groupoids are actually the primitive notions, and in a foundation like that, infinity groupoid, just as a primitive, can actually give a definition of an infinity category that and is simple enough to communicate and with. So all of this existing literature in classical foundations avoids using a definition of infinity category insofar as possible. By having the foundation do work, we can actually start from a definition, and now we're back in sort of more familiar terrain where we have a formal system, and then we formalize consequences of that definition in the formal system. This is how we do rigorous sort of undergraduate level mathematics, not the traditional foundations, but it's a more elaborate formal system that's a bit complicated to explain. So it's based on homotopy type theory. Specifically, I'm going to talk about a simplicial extension of homotopy type theory that has more elaborate context, and I'm not going to describe the formal system at all right here. That's the real obstacle here. It's not that we haven't described it. There's a paper with Mike Schulman where we have, but it just takes a very long time to describe it before you get to the good stuff. I'm going to skip over the formal system and get to the good stuff. So what is the So, I mean, the idea of it, again, is this is actually just based on Martin Luff's dependent type theory, but with a different interpretation of the identity type family. We get rid of axiom K, so iterated identity types can be non-trivial all the way up. And there's a sense in which a type is just like an infinity groupoid, where we can interpret the proofs of equality as paths, and then proofs of equality between equalities as homotopies, and that's where the higher structure comes. And in a particular extension, we equip each type with a second family of arrows. These are Hom types of an infinity groupoid, and so on and so forth. And in this, I haven't described at all, I can actually define what an infinity category is. So what is it? It's a type, so a primitive notion in this elaborate formal system in which every pair of terms Hom from Y to Z, then there is a unique term of type Hom from X to Z that is a composite. So there's data in the witness of composition. Then there's a second condition connecting isomorphisms, which are defined using the category structure, using composition, and paths, which are the terms of the identity types. And so the low-level definition between familiarity with the system. And sort of a low-level explicit definition. What this has to do with identity categories, this is the expert aspect of it, which is that when we interpret the system back in traditional foundations, unique composite says that this moduli space of all composites is contractible, which is what is true. But within the formal system, composition function again. Collapsing the gap. My dream is that if we could do something like this, then we could actually teach infinity category theory to mathematics undergraduates, which would be nice for our colleagues in algebraic geometry and number theory and algebraic topology and other areas of theory, if this could be streamlined somehow. Okay, actually we can formalize, so that definition has been formalized, this whole system has been formalized. The proof written by Niels Rusk, who's the person that most closely mirrors. This is really based on a model of infinity category, not the quasi-category model, but the Rusk space or complete system. What I really like about this approach is that we can already formalize much more complicated theorems about infinity categories than we can in the infinity project. So far in the infinity, we haven't formalized any theorems about infinity categories at all. But certainly, I hope we will by the end of the year. I mean, that project's a little bit newer than this one. But the innate lemma still seems pretty out of grasp. And this is, innate lemma is sort of the fundamental theorem of category theory. This is an explicit goal. Here we can formalize the proof, and it feels a lot more like the undergraduate Unita, or the one categorical Unita lemma. And it's because the formal system is sort of so powerful that we do a lot of work. So what I'm showing you here are, so the Unita lemma says that some type is equivalent to some other type via explicit maps. And here are the definitions of those explicit maps. So given an ambient type term, we can functions from Hom A, Z A to are partial transformations. It turns out that sort of naturality is for free. And given such a function, we can evaluate is A, and the arrow is the identity arrow, and that gives us an arrow from A to B. That's one map in Unita equivalence. That's not difficult to write down in traditional foundations, but more difficult. An arbitrary arrow from little a to B from this formal system. Really what I'm defining here is a function between infinity grids element-wise, given an object and an object and an object. Here's a thing that is nowhere near defined. It's possible to give a definition like this that is not automatically, infinitely, coherently functorial. And so that's what's magical about the system. It makes it feel like I'm doing one category theory. A little more about this. so that was all a bit technical. I want to, well, here again we have adjunctions like at this stage, the cost of and sort of bring this talk back to a higher level. So it's really very painful to elaborate all these higher categorical proofs all the way down to the, if we're trying, are there enough people who are willing to help with wearisome technical work? That's really the, am I going to have to like, 10,000 hours on this, or are people going to be willing to do this sort of stuff that is both complicated, it's expert level work, but technical. Lean is very powerful and it'll only become more so. There's a, but as lean becomes more powerful, as boring technical proofs are replaced by tactics that can sort of automatically handle some of understand the proofs will the people who can apply these tactics be able to understand the proofs if they so right now we're able to prove that would be in lean, and the proofs are conceptual and short, but the formal system is unfamiliar, so it's convincing an expert that these are the correct proofs takes complete. Biggest problem with RZK various other things. In theory, you can formalize any theorem of infinity category theory in lean. That's not at all true, and that's the big issue. The question from the audience. A theorem formalized in RESC is completely useless to user MATLib. Will we ever be able to do this so that somebody could do some derived algebraic geometry? Right now, it's not so helpful to have that in RESC. Formalization will involve a lot of specific formal systems. My experience is it is kind of nicer to use these synthetic languages, but we have these sort of AI-powered tools that really make it a lot easier to formalize in lean. Will that ever help cubical AGDA or some other sort of smaller experiment? In the production of formalized mathematics, should understand humans. Okay, I'll stop there. Thanks.
Thanks for the nice talk. I'm curious what your vision is for peer review of mechanized proofs. I think in the POPL community we kind of have this separation where we review the papers and we sort of trust that if they say, oh, all of these theorems have been mechanized, we accept the paper, and then we, after the fact, maybe do this artifact review process, but only after the paper's been accepted. So I'm curious how you see formalization changing the landscape both for us, but also for the mathematics community.
Yeah, that's a great question. I only have one experience publishing within the there's aspects of it that function much better in mathematics. I mean, it's a real issue. A typical paper in this field will be 100 pages long and, will involve some sort of sketched argument. So it's completely unfeasible for that something is correct. Getting papers reviewed at all, finding publication years. A lot of things are just languished as preprints forever because people just don't want to go through this. I can imagine is just sort of forcing authors to do a little bit more. So beyond mathematicians right now, and it is an important question. Of course, mistakes can be made in the formalized definitions, and but I think rather than complete formalizations, and it will definitely help us like clean up our act.
Yeah, I have a question. So the slide that you showed with like basically the analytic approach and then what you called like option 1 or option 2, I don't remember. So from a computer scientist perspective, this analytic approach, it looks a lot like if you think about set theory as kind of your machine code, then your option 1 is to define your abstraction basically at the level of machine code, and nobody wants to program machine code, which is why, like as you mentioned, that there's this quasi-category definition, and like maybe not a lot of things have been proved about it. Then option 1 is basically a high-level programming language. So you're mentioning Lean, and then option and so the Infinity Cosmos project that you mentioned, to me, it looks like you're trying to define something like an embedded domain-specific language inside of a high-level language, which would be Lean here with its foundations. And then option 3 is basically defining your own programming language, essentially with its own foundation, with all of the project problems that, of course, causes to come about, like what you mentioned, that you can't maybe interoperate with other domains of mathematics that might use different foundations. So in general, for a lot of this talk, I had the idea that the way you're describing these problems in mathematics, they're becoming more and more just like things, like computer science problems. So how do you feel about that? Is that a development that you like, or are you apprehensive about it? How do you think mathematicians feel about this development?
Sorry, your mic's not working.
My mic is off. Okay, apologies. Thanks for that translation. I appreciate it. I do feel a bit uneasy because I feel like now that I'm involved in formalization, I understand my work a lot. I mean, there's some senses in which I understand my work better. I understand proofs at a much more fine level of detail than I ever have before. But I feel more dependent on, frankly, the computer science community to achieve anything at all. And there's these issues that I'm running up against, and developing an API to support a definition that I just have absolutely no idea how to proceed. I think we are going to see a lot greater integration between mathematicians and computer scientists, because we absolutely cannot do any of this formalization of serious mathematics without a lot of help. And any work that you all can do to make yourselves easier for us to understand would be really wonderful, because yeah, I think a lot of people are kind of uncomfortable right now, and we don't want to just know that you've solved the problem, but we want to understand how you've solved the problem, because it's just very uncomfortable for us to be reliant on stuff that we don't understand to prove a theorem. So.
Anybody else?
So infinity groupoids are, of course, a special case of infinity categories. And so I was wondering, like, this seems like it should imply that a type theory with a model in quasi-categories should subsume a type theory with a model in, say, infinity groupoids. So are there any hurdles to this in practice? Like, if I have a proof in homotopy type theory, univalent type theory, does that immediately translate to a proof in something like RESC?
Right. I won't pretend to understand every possible way that you could develop a synthetic domain-specific language for type theory, but it is true that proofs in HOT are proofs in RZK. So, and the models of RZK are in particular infinity topoi. So places where HOT also has a model, they're infinity topoi of simplicial objects in an infinity topo. So. So yes, but what you're saying is right. And one of the challenges in using RZK, so the language kind of looks like Agda, but it's a different type theory. We were not able to import HOT proofs from anywhere, so we had to spend a whole bunch of time reformalizing for ourselves a whole bunch of stuff in HOT to use as kind of the background, basically set theory and logic for what we were trying to actually do. So I'd be very happy to discuss some details of these proof assistants and the implementations in more detail later, but maybe that's a better one-on-one conversation. Thanks again.